Alright, so in this video we're going to take a look at explaining some scenarios in terms of energy and in terms of momentum. And these are some specific scenarios designed to identify how well you understand these concepts. So let's start with question 1. You lift a suitcase from the floor to a table, and in addition to the weight of the suitcase, select all of the following factors that determine the work done by the gravitational force of the suitcase. So statement 1, whether you lift it directly up to the table or a longer path. So it's saying if you take a longer path, that might affect the amount of work done. Whether you lift it quickly or slowly, so the amount of time taken, or the height of the table above the floor. So pause the video and have a crack at this question, then we'll take a look. All right, so now you've got your answer. So the principle we're using here is the principle of conservation of energy that states the work done is equal to the change in GP plus the change in kinetic energy. So we haven't been told anything about speed, so we're just going to think about it in terms of GP. So to get the work done, we're going to need the force, the weight force, which is the thing we had already. And the only other thing we clearly need is the height change. It doesn't matter how quickly it happens or what path it takes. The only thing that matters is what the height change. So it's going to be 3 only. Okay, so question 2, we've got 2 frictionless slides shaped differently but with the same start height, and they finish at the same level as well. You and a friend have the same weight force, slide down from the top, but we've gone on different shaped slides. Which statement best describes who has a larger speed at the bottom of the slide? So pause the video and select your answer, then we'll take a look at it. Alright, so the principle we're going to be using is again conservation of energy. This time there's no work done by external forces, so we can make the change in GP equal to the change in kinetic energy or the negative of it. So we can put in, so the change in height is minus h, so that becomes a plus mgh, and the change in kinetic energy is going to be half mv squared minus 0 because we started at 0. And so you can see here that because you have the same height change, we're going to have the same speed at the bottom. All right. So a moving white hockey puck collides elastically with a stationary red hockey puck on the frictionless horizontal surface. No net external force acts on the two-puck system. Select all the following statements that must be true for this collision. So the statements are: 1, the kinetic energy of the white puck is conserved. Same before and after. The linear momentum of the white puck is conserved. The linear momentum of the two-puck system is conserved. So pause it, select your answer, and then we'll take a look. Okay, so if there's no external force acting, we can apply the principle of conservation of momentum. So initially, only the white puck is moving, so we only have 1 momentum term. But after the collision, we're now going to have 2 momentum terms because they're both going to be moving. So what we can do is we can also apply the condition of the elastic collision, which states that the total kinetic energy is conserved. So first of all, we know statement 3 is going to apply because there's no external force. So 3 is going to be correct. The white puck is going to transfer some of its momentum or some of its energy to the other puck. Therefore, its momentum is not conserved. And it's going to and also its kinetic energy is not conserved. So we can see that it's going to be B. It's 3 only. All right. Okay, so for the next question, we've got 2 identical stones, so same mass, same size. They're shot from the cliff from the same height and with the same speed. One shot vertically upwards, the other shot vertically downwards. Which one of these statements best describes the speed when it hits the ground? So pause the video and select your answer. All right, so let's look at the principle we have to use here. We're going to apply conservation of energy, and we're going to assume there's no work done by external forces, or if there is, that it's about the same for both. So assuming that, we can make the sum of the change in GP and the sum of the change in kinetic energy equal to 0. And we can put expressions in for the change in kinetic energy and change in GP. So GP is negative because it's going to be decreasing. And we can rearrange that to make the velocity, the final velocity, v the subject there, or at least the final kinetic energy of the subject. And we can see from this equation, they have the same starting height, they have the same starting speed, they have the same mass. Therefore, they must have the same final speed as each other. So that's going to be option 4. All right. So we've got two identical bullets fired horizontally at the same speed, but one of the blocks it's fired at is steel, one of the blocks is wood, but they have the same mass. So the blocks rest on a frictionless horizontal surface, and the bullet is going to bounce off the steel, and the bullet is going to get embedded in the wood. Which of the following statements best describes which block travels faster after the collision? So pause it, select your statement, and then we'll take a look. Okay, so we're going to use Newton's laws to understand this one. So the force that acts on the bullet will be able to change in momentum of the bullet divided by the time in which that happens. So for the wood, it's going to become embedded in it, so it's going to end up at the same speed as the wood. So I've called that v wood. And it started at v0, so we get an expression for the force on the bullet, and using Newton's third law, the force on the wood must be equal and opposite. Then we can do the same process for the steel, and this time what's going to happen is it bounces off the steel, so its momentum becomes negative. So then when we rearrange this expression, we can see that the force on the steel is going to be much bigger because there's been a bigger change in momentum. So we'd expect the steel block to travel faster after the collision. So we expect the steel block to move faster. Okay, so we've got a satellite moving around Earth in a circular orbit at constant speed. The only force that acts on the satellite is Earth's gravitational force, which points directly towards Earth's center. Which of the following statements is true as the satellite moves from point A to point B in the orbit? So pause it, select your answer, then we'll take a look. Okay, so we're going to think about how work done is calculated. So you should know the force acting on the object is towards the center of the circle, towards the center of the Earth, which means the force and the displacement are going to be perpendicular to each other. So in the work done is Fs cosine theta, that means theta is 90 degrees, which means no work is done. Therefore, what we can say is go for option C, that there's no work done by the gravitational force, which is the centripetal force in this particular example. Okay, so we've got a motorcycle and a truck moving in the same direction next to each other on a highway. The speed of the motorcycle is 4 times as large as the speed of the truck. At the instant, the motorcycle is accelerating forward while the truck is moving at constant velocity. Which one of the following statements best describes which vehicle has larger momentum? So pause it, select your answer, then we'll take a look. All right, so to calculate momentum, we need the mass and we need the velocity, and we haven't been told what the mass is, so we don't have enough information to solve this question. Simple as that. Okay. So you want to lift a heavy block through a height h by attaching a string of negligible mass and pulling it at constant velocity. You have a choice of lifting it by pulling the string vertically or lifting it up a frictionless inclined plane. Which of these statements is true? So again, pause it, select your answer, then we'll take a look. All right, so in the first example where you lift it vertically, the tension force in the string is just going to be equal to the weight force. In the second example, the tension must be equal to mg sine theta, the component of the weight force parallel to the slope. So that means that when we now going to start thinking about work done, we're going to need to do the same amount of work because they are lifted through the same height. Therefore, we're going to have to essentially have the same work done by the tension force in either case because they're both lifting it through the same height. That's the key. It doesn't matter that the forces are different size. What matters is the energy change. Okay, so 3 bicycles approach a hill as described below. So cyclist 1 stops pedaling at the bottom of the hill and lets her bike coast up. Cyclist pedals so her bicycle goes up at constant speed. Cyclist pedals harder so the bicycle accelerates. So we're going to ignore the effect of friction against the motion. State all the cases where the total mechanical energy of the cyclist and bicycle is conserved. So pause it, select your answer, then we'll take a look. Okay, so total mechanical energy would be conserved if there were no external work applied. So if the cyclist is pedaling, they are applying external work. Therefore, that would not be an expression of total mechanical energy being conserved, because they're transferring some of their internal chemical energy into these forms of energy. So the only one that works for this is 1, where the cyclist has not applied any force and therefore hasn't increased the total energy of the system. Okay. So we've got a bomb at rest on a horizontal frictionless surface. It explodes and breaks into 3 pieces that fly apart horizontally, like in the diagram. Select all the statements that must be true after the bomb has exploded. So pause the video and select the statements you think are correct. Then we'll take a look. All right, so the statements that you should have picked are statement 2 and 3. So initially the kinetic energy is 0, and afterwards their parts are moving, so they have kinetic energy. So that's definitely not the same before and after. However, there's been no external force acting. Therefore, the total momentum must be the same before and after, so 2 works. And you can see to start with, the momentum is 0, so therefore the momentum after must be 0 too. So that gives us 2 and 3. Okay, so you and your friend are both standing on a horizontal frictionless surface. To get your friend's attention, you throw a ball due west at your friend as shown below. The ball bounces elastically off your friend's back. Which one of the following statements is true about the situation? So pause it, have a read, and select which one you think. Okay, so we are going to be essentially applying conservation of momentum because there's no external force being applied to this system. So when you're standing there holding the ball, you have a total momentum of 0. So when you throw the ball to the left, to make sure the linear momentum stays the same, you must go to the right, which will be in the east direction there. So using a rope of negligible mass, you pull a box along a horizontal surface with a constant force Fa. The box moves at constant velocity from position A to position B. Force of friction Fk cannot be neglected. Which one of the following statements concerning the motion of the box from A to B is true? So select your statement and then we'll take a look. All right, so we are going to be thinking about this in terms of conservation of energy. So there's been no change in height because it's traveling horizontally, and there's been no change in speed, so there's no change in kinetic energy. So that means that the work done must be 0. And what that really means is the work done by A must be equal to the work done by K, because then we'll get a net work done of 0, which is what is described by option D. Okay, so cart A and cart B are identical in all respects before the collision. So cart A starts from the rest on a hill at height h above the ground and collides head-on with cart B, which is at rest on ground level. The 2 carts then stick together. Carts A and B are at rest on opposite hills at height h over 2 above the ground. They roll down, collide head-on, and stick together. And so we want which one of the following statements is true about the 2-cart system just before the carts collide in each case. So pause it, take a look, then we'll go through. Okay, so the correct answer is the kinetic energy is going to be the same in both cases, and the reason is the starting GPE is the same in both cases. So we can see that A in the first example has a height h, and in the second example, both of them have heights of h over 2, so their GPs add together to give the same, therefore their kinetic energy must be the same. Which one of the following statements is true just after the carts collide? So again, pause, have a think and select your answer. Alright, so the correct answer is D. The momentum of the system is non-zero in case 1, while it is 0 in case 2. The reason being, in case 2, the carts will have equal and opposite momentum, so they will cancel each other out, giving you 0, whereas in the one on the left, when A collides with B, they're going to move off together to the right and have some momentum. Okay, so while in a playground, you and your niece take turns sliding down a frictionless slide. Your mass is 75 kilograms, your niece's mass is only 25, so 1/3 of your mass. Assume that both of you begin sliding at rest at the same height. Which one of the following statements best describes who has the largest speed at the bottom of the slide? So take a look through your options and select your answer. Alrighty, so if we have a look at this situation, we have the same starting, we don't have the same starting GP anymore because you have more mass, therefore you have more GP to start with. However, because you have more mass, you end up with a higher kinetic energy as well. But when we put the two parts into the equation, we see the masses end up cancelling out and don't actually matter in terms of the speed you end up travelling at. So the answer we should go with is you both reach the same speed at the bottom. Okay, so two small spheres of putty, A and B, of equal mass hang from the ceiling on massless strings of equal length. Sphere A is raised to a height h0 as shown below and released, collides with sphere B, which is initially at rest. They stick and swing together to a maximum height hf. hf can be determined in terms of h0 by invoking which of the following principles? Conservation of mechanical energy, conservation of linear momentum. So select which one or both or none you think would be necessary. Okay, so the principles we're going to need is both of them. So to figure out the velocity with which A collides with B, we're going to need conservation of mechanical energy to turn GP into kinetic energy. Then to deal with the collision between the two, we're going to need conservation of linear momentum to figure out their combined velocity afterwards. And then we're going to need conservation of mechanical energy to figure out the final velocity of the combined object once the collision has occurred. So we need 1 and 2. So you drop a ball from a high tower and it falls freely under the influence of the gravitational force. Which of the following statements is true? So have a look through the statements, pick your answer. All right, so the answer that we want is B. So the way we can relate this is by thinking about the energy transfer going on. So we know the kinetic energy is going to equal to the loss of GPE, which is going to be equal to mgh. Therefore, we can see that the kinetic energy is directly proportional to the height, or it's going to increase equal amounts over equal distances. They mean the same thing. So, got two parts here. So let's start with 18. Which one of the following statements is true concerning linear momentum? So have a look through, then pick your answer. All right, so the one we are going to use is we should know that impulse is equal to the change in momentum. So that means that they must have the same unit as each other, which would be either Newton seconds or kilogram meters per second. The brakes of your bicycle have failed, and you must choose between slamming into either a haystack or a concrete wall. Which one of the following statements best justifies why hitting the haystack is a wiser choice than hitting a concrete wall? So have a look through your options, then take a look. So the principle I use to solve this is Newton's second law. Force is equal to the rate of change of momentum. So regardless of which of them you hit, you're going to have the same change in momentum because you have the same starting speed. So the key is going to be the time taken for that change to occur. So If you hit a haystack, haystack is soft, so your collision will take longer. So that's why it gives you a smaller force, because it takes a longer time to slow you down. So you slide down two consecutive slopes that we can see on the diagram. Both are frictionless ice, and both have a height change of h. So select the following statements that must be true. All right, so now you've got your answer. Let's take a look. So we're going to be using the conservation of energy, as we have done several times. So we can see that for each of them, their change in GP is going to be the same because they've got the same change in height. So what that means is that the work done by gravity will be the same in each case, because that's what GP is. It measures the work done by the gravitational force. So we should have that they'll be identical for both sections. Okay, so rain's falling vertically down into a cart that has frictionless wheels, and it's initially moving at constant velocity on a horizontal surface. The raindrops come to rest with respect to the cart after striking it, and the rainwater collects in the cart. Select the following statements that must be true about this situation. So have a read through, select your statements, and then we'll have a look. Okay, so this problem is about conservation of linear momentum. So when the raindrops land in the cart, they will exert a force downwards on the cart because the raindrops experience a force and a change in momentum upwards. This means that no external force is acting in the horizontal direction, which means linear momentum is conserved horizontally. So as the rain collects, its mass clearly increases, therefore its velocity must decrease to conserve momentum. That means we're going to need statement 3 to describe this system. So if we have a look at statements 1 and 2, statement 1 says it's constant velocity. That's not true. And so does statement 2, so that can't be right, so it's just 3. Okay, so 3 balls are launched from the same horizontal level with identical speeds v0. Ball 1 is launched vertically upwards, ball 2 at an angle of 60, and ball 3 at an angle of 45 degrees. In order of decreasing speed, rank the speed each one attains when it reaches the level of the horizontal dashed line. All of the balls have sufficient speed to reach the line. So select your answer, then we'll take a look. Okay, so this is a conservation of energy type question. And again, we've got no work done by external forces. So what's going to happen is the kinetic energy is going to transfer to GV. So they all have the same starting kinetic energy. Therefore, when they all gain the same GP, they'll have the same final kinetic energy. So we're going to have the same speed at the end. Okay, so 23, you drop 2 balls of equal mass made of rubber and putty from the same height h above a horizontal surface. The rubber ball bounces up after it strikes the surface, while the putty ball comes to rest. Assume that in both cases the velocity of the ball takes the same time to change from its initial to its final velocity due to the contact, so the same collision time essentially. So what we're going to do is describe the relationship between the two forces. So have a look at the few options and then we'll take a look. Okay, so we're going to use Newton's second law to explain this. So the rubber ball is going to bounce off, which means if we say it started with positive momentum, afterwards it's going to have negative momentum. So it's going to have a bigger change in momentum than the putty, which becomes stationary. And therefore, that means the force on the rubber must be greater than the force on the putty because it's had a bigger change in momentum. Okay. So, question 24. 2 blocks are initially at rest on a frictionless horizontal surface. The mass of block A is less than the mass of block B. You apply the same constant force and pull the blocks through the same distance along a straight line as shown, and they're applied over the entire distance. Which of the following statements correctly compares the kinetic energy of the blocks after you pull them the same distance? So have a look through and then pick your answer. Okay, so the key to this is the work done is going to be equal to the change in kinetic energy, and work done is force times distance if the force is constant. So if there's the same force over the same distance, they must end up with the same kinetic energy, so it's option A. A box slides with initial speed v0 on a horizontal surface with friction and eventually comes to a stop. Which of the following is equal to the change in the kinetic energy of the box? So I'm going to approach this using units. So I'd like to have a go at this question, see if you can figure it out, then I'll show you how it's done. Alrighty, so first of all, the unit we're trying to get to is kinetic energy, so joules, which can also be expressed as a Newton meter or a kilogram meters per second squared in base unit. So momentum times distance would be, momentum is Newton seconds, distance is meters, so it gives you Newton meter seconds, which is clearly different to Newton meters. We've got momentum times time, which will be Newton seconds times seconds, so Newton seconds squared, so that doesn't work. We've got momentum times deceleration, so newtons times meters per second squared, so that's not the same. And then we've got mass times acceleration, which is a force. So the correct answer is none of the above. So that concludes this video, taking a look at some concepts in energy and some concepts in momentum and Newton's laws. If you have any questions about any of these individual questions, please do comment and ask me, and I'll get back to you as soon as I can. But thank you very much for taking the time to watch.